Welcome everyone to the Power Measurement and Analysis using Agilent InfiniiVision X Series Oscilloscopes webinar. Today we'll hear a presentation material from Johnny Hancock. Johnny's a product manager with Agilent Technology Oscilloscopes product division. He began his career with Hewlett-Packard in 1979 as an embedded hardware engineer and holds a patent for digital oscilloscope amplifier calibration. Johnny is currently responsible for worldwide application support activities that promote Agilent's oscilloscopes, and he regularly speaks at technical conferences worldwide. For everyone's comfort, this is a lecture-style meeting. However, you can send questions in writing at any time during the session through the Q&A functionality of the WebEx meeting. We'll do our best to answer your questions during the session, but we may need to come back to you later if we run out of time. While the answer to your question may be published for others to see, we'll keep your identity private. Please note that this webcast will be recorded so you can review and share with your colleagues at any time. And with that, I'll hand over to Johnny.
Thank you, Art. Well, let's get started, and let's take a look at our agenda slide and see what we're going to talk about here today. First of all, I just have a rhetorical question here. What do all of these products have in common? Now, since this is not a live seminar, I'm just going to click to the next slide, show the answer. Well, they all have a power supply. Every electronic product must be powered up, and they typically have a power supply in them. And it's very important to make measurements on power supplies to make sure they meet your specifications. So let's take a look at our agenda for today. First of all, we're going to just briefly go over some power supply and measurement basics. But the focus of our webinar today is we're going to be showing several examples of different measurements that we suggest that you perform on your power supply if you're specifying a new power supply for your product or you're designing one to make sure that it meets your requirements. So we'll be talking about various measurements on input characterizations, switching characterization, as well as output characterization. So let's get into some basics. First of all, let's talk about what some of the trends are today when it comes to switching power supplies. Now, in a minute, we'll talk about the different types of power supplies, but really our focus today is on switching power supplies. And the trends are improving efficiency. People want to get the most out of their power supplies without having wasted watts and wasted joules. Engineers want to increase the power density, so how much power can I get out of a power supply given for a given amount of real estate or area on your board. Decreasing thermals, well, if you waste a lot of energy, you're going to generate more heat. It's going to require you to put in more cooling. Of course, everyone wants high reliability. They don't want their products breaking down and incurring warranty cost. This is a big one, controlling EMI, and this is especially important for switching power supplies. And we'll talk about what some of the trade-offs are, and one of them is they generate more noise than a linear power supply. And of course, people want to reduce the cost as much as possible. And all of this adds up to increased test time for you if you're either a power supply designer or one that specifies for someone else, and then you get your power supply and then must test it. So what is the job of a power supply? Well, it's to produce a well-regulated, low-noise DC output. And there are basically two different types of power supplies. There's the linear power supply and the switch mode power supply, typically just called switching power supplies. There are advantages and disadvantages of each. Now, years ago, there were only linear power supplies. Some of the advantages are they do have low noise. They can be very well regulated. It's relatively easy to filter them. However, they're only step-down type nature, so you can't have a given input voltage and then step it up to a higher voltage. It's always step down. But this is the biggest drawback. They're very inefficient. We could add a few more negatives. They're more expensive, they're heavy, and they can generate a lot of heat if they're not very efficient, wasted heat. Most products today have switching power supplies in them, as I mentioned earlier, often called switch mode power supplies, SMPS. The technology, and we'll talk a little bit more about this, although this is not the focus. We're not going to get into the theory of designing power supplies. But the basic theory is they switch on and off, typically at a rate 20 to 200 kilohertz, sometimes higher than that. And the advantage are they are very efficient. You can generate a lot of power in a small package. There's a variety of topologies, but this is the big negative. They can have moderate to high noise and output ripple. And so you've got to make sure that it still meets your requirements. Now, some real basics when it comes to power, and I'm sure if most of you are probably familiar with Ohm's law, volts equals amps times resistance. Instantaneous power, power is equal to volts times current. Now, we can take a combination of these, and we do in our oscilloscopes when we make measurements, such as power equals I squared times R. Now, some other terms, there's real power. So there's not just one type of power. There's real power, which here you can see is the vector. If your system is purely resistive, it's going to be all real power. But there can also be reactive power. Typically, power supplies can have inductive and capacitive elements, which means there's going to be reactive power measured in units of volt-amp reactance, complex power, and apparent power, which is the absolute value of complex power measured in volt-amps, and that's the vector sum of the real power and the reactive power. So let's take a look at a very simplified diagram of a switching power supply. Here we show an AC input for you folks here in Europe, since this who this webcast is primarily focused on. That'd be 230 volt AC RMS. Where I'm from here in the U.S., it'd be 115 volt AC. The input goes through a full wave rectifier, typically some sort of crude filtering, not highly filtered, and then that is sent through a switching transistor, which switches on and off at the switching rate. And the theory behind it is, and we'll show this in a few more slides, when the transistor is on, you have very low voltage across the transistor, and you have current flowing. When it's off, and so then you can take volts times amps. Ideally, it's going to be 0. And then when it's off, you have high voltage across the transistor, 0 current. 0 current times volts is 0 power. So that is often it's a transformer coupled out and then rectified again, and ultimately you get your output voltage. Now here we list some of the key and most important measurements. Input analysis, you want to measure the power quality, current harmonics, inrush current. We'll show examples of each of these in a few minutes. And then you want to do analysis on your switching circuitry. You want to see how much losses are occurring. And probably that's the most important measurement. Modulation analysis, slew rate, and safe operating area. And then on the output, probably the most important measurement is you just want to see the quality of the output ripple. And then there are several transient type measurements: turn on time, turn off time, transient response. And this is somewhat of a unique measurement that's typically not available using an oscilloscope, which that's the tool we're focused on today. And we'll show this in a few minutes. Power supply rejection ratio. And then the bottom line is the efficiency in output versus input. So let's get into the switching part of it. The key element, typically it's a MOSFET type resistor, although it could be a bipolar type transistor. When the transistor is on, it's conducting. Again, as I mentioned, ideally, when it's fully on, the voltage across the transistor is 0. Therefore, if current's flowing, you got 0 volts, you got 0 watts. And then when it switches off, ideally, again, you got 0 current. So again, power equals volts times 0 current, you get 0 watts. Now that's the ideal situation, but that's not quite reality. So let's take a look at some switching signals. Here we show current flowing. So this is the on state. There actually is some small amount of voltage called VDS. That is, if it's a MOSFET type resistor, that would be the saturation voltage. And so there is some small amount of power that's being lost during that phase of the on state. And then when the transistor switches to the off state, you go through a phase called the turn off phase. This is when the transistor is actually conducting in its linear range, in which case it is not fully on or fully off, and this is typically where most of your losses occur, power and energy losses. And if you look at the power waveform, which is simply volts times amps, you'll see an impulse during that short period of time. Now, we've exaggerated it here. I'll show you in just a few minutes what it looks like on an oscilloscope. This would be a very short spike, and this is where most of your energy losses occur. Then you have the off state, and in this case, current is 0, and then you have volts, and typically there is 0 losses during the off state. Then there's another switching state. Again, you go through the linear phase of the transistor, and there are power losses. So this is what these waveforms actually look like. They don't look like those square waves I just showed in the previous one, and it really depends on the topology of the actual switching power supply. The yellow waveform here, I'm showing the voltage across the transistor, and this between this here and here is where voltage is near 0, not exactly 0, and where current is flowing. So this is what we call the conduction phase, and there can be losses during the conduction phase. The purple waveform down here is the instantaneous computation of volts times amps, and typically a scope has waveform math capability. You can multiply them to produce the power waveform. Now, at this point right here is where the transistor is switching from on, so current is high, goes to 0. Voltage is low, goes to a high level, and that's where it switches, and in this case it is switching off. And right here, if you look very closely in a purple waveform, you can see a very narrow spike. Same thing here. Now, what we can't see is when the other switching state on this particular power supply, there should also be a very small spike here. And so this is where most of the losses are occurring. So let's now take a look at some of these measurements. We're going to begin by looking at some of the input analysis measurements. And we're going to step through almost all of these and show you what they look like on an oscilloscope. Now, this is the list of measurements that are available on Agilent's InfiniiVision series oscilloscopes. We've organized them based on input, switching, or output type measurements. There are some unique measurements that are available in our scopes that are not available in many other vendor scopes, particularly some of the what I would call transient or single shot measurements, inrush current, turn on, turn off, and transient, and this is probably the most unique measurement that I don't think you'll find on any other oscilloscope, and that's power supply rejection ratio. We'll get into that in just a little bit. Before you begin any measurements, what's very important, especially for the switching measurement, is deskewing the probes. Now, here we show you can see a current probe. This is a clamp-on type probe. That's a typical type of current probe you're going to use for these measurements. And here we show, you can't see the high voltage differential voltage probe, but here you can just see where they're connected. There can be different lead lengths between the current probe and the voltage probe, and there can be skew. Now, you can automatically deskew these probes. This is the fixture that we provide, and you can just press a button, and here we show the voltage waveform ramping up, the current waveform ramping up. They should be aligned. If you do the deskew, it will automatically align them so that you can make very accurate measurements. So let's first take a look at some input line analysis. So this is where you're actually characterizing, making measurements on primarily your AC input. One measurement is power quality. That's where the scope will automatically measure real power, reactive power, apparent power, phase angle, power factor, and crest factor. Current harmonics. The current harmonics is actually the only test amongst all these tests that I would term as a compliance test. That means it must meet a particular standard. and then inrush current. Now, let's take a look at each of these and how you perform them on an oscilloscope. If you're using one of our competitor scope, you're going to see similar results, and so you just have to take what I'm showing you. This is particular to an oscilloscope. So the first thing is simply select the power quality measurement within the analysis menu. And then we have a menu called Signals. And this is something that's somewhat unique about our scopes. It will bring up this connection diagram, and it gives you instructions on where to connect the probe. So here we show a little diagram of the scope and the differential high voltage active probe. It shows you where to connect that probe as well as the current probe. And then you can just simply press Auto Setup, and the scope will automatically scale the waveforms. In this case, you can see the yellow waveform is the voltage waveform, the AC input. The green waveform is the current waveform, so it will perform optimum scaling, and then also turn on the waveform math function to compute the power waveform. Now, if you don't have an automatic power measurements in your oscilloscope, you can do this manually. It just takes a little bit more time. And then it automatically turns on and provides answers for real power, reactive power, paired power, power factor, phase angle, and crest factor, which is equal to peak over RMS. And here you can see the results on the screen of the scope along with statistics. So if you're running this measurement continuously, you can see if there's any variations going on. Now again, if you don't have a power measurements option that automates this, you can actually perform these measurements manually. It's not easy. Real power is not too bad. You just take the all scopes, I think today, you can they have waveform maps, so you can multiply channel 1 times channel 2 in this case and get the power waveform. And then to get the real power, it's simply the RMS over N cycles of the power waveform. The apparent power is you can measure the volts RMS over N cycles, current RMS over N cycles, and then multiply those two. Reactive power is a little more difficult, and but you can get to it, but again, it's more difficult. Well, let's move on to the next measurement, and this is, I mentioned earlier, is one that is considered a compliance test, and what it is current harmonics. It's what type of harmonics are injected back into the AC line input. The standards were established. They're called the IEC standards. Were actually established in the European Union, and there are different classes. There's Class A, Class B, Class C, and Class D. It depends upon the type of equipment. Is it a kitchen appliance, or is it a PC? And it depends on what type of end product it is as to what type of classification and specifications it must meet. What the scope does when you perform this measurement is it performs an FFT on the current input current waveform, and then it must meet, it checks the harmonics, the first harmonic all the way up through the 40th harmonic. And here you can see the results in two different ways. Here we show the various limits in a tabular format for each of the harmonics. And here we can see the scope indicating whether or not it passes or fails. Now, in this particular screen image, we can see the first through the 9th harmonic. You can then take this scroll bar and scroll down and see up to the 40th harmonic. Alternatively, you can choose to see it as a bar chart to show you each harmonics. If any of the harmonics fails, it will highlight them in red. Here we're showing them in everything is passing in green. So this is a very important measurement. If you want to be able to sell your product within the European Union, it must meet these standards. Inrush current is another input line analysis. Now in this particular power supply that I was measuring when I captured these screenshots, the green waveform here is the current waveform. The steady state amplitude or maximum current was less than an amp. But when you initially turn on a power supply, there will be a surge of current, especially if there's capacitive elements there. So again, you select the input inrush current measurement, select signals, and here we get the same diagrams. Our connections are still the same. Now this is a single shot measurement, so there is not a key like I showed earlier where it says auto setup. The only way auto setup will work is if there's a repetitive signal. But what the scope does is it gives step-by-step instructions, which I'm not showing here on screen. Instruction will come up on screen when you press the apply button, and it will tell you to turn off your power supply. Then it says, then press next. You press next, and then it will say, turn on your power supply, then press next. And the scope automatically then sets it up to capture that single shot transient and measures the peak current. So in this example here, the peak current measured nearly 30 amps. Now this particular measurement should probably be repeated several times. Sometimes you'll see a large positive surge of current. Sometimes you'll see a large negative current. And it's going to vary the amplitude, and it actually depends upon when you flip that switch, the phase of the input signal. And so you may want to repeat this measurement several times to find out what the absolute maximum peak current is and whether or not it meets your standards. Now let's get into the switching analysis, which is many consider the more important measurement to improve efficiency. As I mentioned earlier, there are several important phases of switching analysis. There's the turn on and turn off phase, and that's where the transistor is going through the linear range. And then there is a conduction phase, and that's where when the transistor is conducting, there is a small amount of voltage across the transistor, and there are losses during the conduction phase. There's actually another phase that I've not listed here, and that's the non-conduction phase. And this is pretty reliable, that when the transistor is off, there is zero current flowing, and there is typically no losses during the non-conduction phase. Another important measurement is slew rate, and that just simply measures the rate of change of your switching signals when they change from on to off and off to on. Let's take a look at some of these measurements. So again, you select your switching loss measurement, and then select the signals, and here we show a different diagram that pops up on screen. Gives you step-by-step instructions on how to connect the probes, and here we show it connecting the differential active probe across the transistor and the current probe, in this case connected at the source of the transistor. You could also connect it up the drain. It's going to be the same current. Again, press the auto setup, and the scope will automatically scale in the what we call the main time-based window. That's the upper portion. It's going to scale for 2 switching cycles across screen, and then it will turn on the zoom display. That's between this point and this point. It scales for 1 switching cycle. You press the apply button, and then it turns on the current. It turns on the power waveform, which is the instantaneous multiplication of the volts, which is the yellow, times the current, and then you get the purple waveform, which is the power waveform. And then it automatically measures power loss and energy loss. Now let's take a little bit closer look at some of these waveforms. Again, between this point and this point is when current is flowing and voltage is very low, near zero. And I just want to highlight a problem that we have here. This voltage waveform is typically a very high voltage waveform. Now in case of this power supply I'm testing, I think it was in the range of something like 40 volts, but it could be in the range of hundreds of volts. If you want to measure this voltage accurately, the problem with the oscilloscope is you cannot measure this voltage accurately at the same time. We just don't have enough resolution and accuracy. Now you may say, well, why not just get a scope with more bits of resolution? Well, that would improve the resolution of the measurement, but it would not improve the accuracy. All scopes have a certain amount of what you might call offset accuracy. In the old analog days, we called it balance accuracy. So when you put a waveform trace across screen, maybe it's 0 volts, you might see a 1/10 of a division or a 20th of a division of offset. Well, when you're making this measurement, a 1/10 of a division of error is significant because this is a very low voltage waveform. And the problem is, so that means the power waveform is inaccurate. It makes it very difficult to make an accurate measurement of the losses across the conduction phase. So let's show some other ways to make this measurement. First of all, if you want to measure the losses just during that linear portion when it's switching, you can zoom in using the zoom time base on just that impulse of power and make a very accurate measurement on that power loss. In this case, we're getting about 69 milliwatts. Now, alternatively, you can also zoom in on just the conduction phase. But in order to make a more accurate measurement on the losses during the conduction phase, what a lot of scope vendors recommend, as well as Agilent, is rather than computing the power based on volts, or current, which is the green waveform, times volts, which is the yellow waveform, you can input what we call RDS. Worst case, what is the resistance of that transistor when it's turned on? In this case, I've set it to 200 milliohms. It can typically be a lot less. In this case, what the scope does dynamically is it will compute the power in different phases using different methods. So during the conduction phase, it will compute the power as I squared times R, and the purple waveform you see is the power waveform. Now, this is a much more accurate measure of the power. In this case, our relative power loss during this phase is 34 milliwatts. Now, where do you get these values RDS on? Typically from a data sheet for that particular device. In this case, here you can see worst case 7.5 milliohms up to 9 milliohms. These are the factors that you could enter and then make a more accurate measurement of the power losses during the conduction phase. Now, another measurement is slew rate. Now, one way you can reduce the amount of power loss, again, I mentioned earlier, the phase you are typically losing the most power and energy in a switching power supply is when the transistors are switching on and off. And if you can improve the slew rate, a faster switching time, then you can decrease the amount of power loss during that phase. But there again, there are other trade-offs. If you go to a faster switching time, now you run the risk of having more transients on the output and more output ripple. But again, it's an important measurement. Again, you can press the signals. It shows you how to connect the probes. Again, it's the same as it was for the switching measurement. And the scope will automatically zoom in on the switching phase. So here we can see a zoomed in of the transistor, the voltage ramping up and the current ramping down. And the scope will automatically turn on the DVD math function, which is the slew rate of those signals. The peak of the purple waveform here, that's the maximum, is the maximum slew rate, in this case of the voltage waveform, and we're measuring about 1.7 gigavolts per second. Sometimes instruments of the measure it in terms of volts per microsecond. We measure it in terms of just volts per second, in which case you get gigavolts per second. You can also change to select current, and in which case it would measure DI/dt, in which case you would probably be looking at the minimum if it was switching off. So that's the slew rate measurement. Output ripple is important. If you want a very well regulated output, you want as flat as possible. As I mentioned earlier, one of the drawbacks, the negative things about a switching power supply is they are noisier. The switching signals can couple onto the output, and you have to be very careful about filtering that. Let's take a look at the measurement. Again, go to the signals menu. This is probably one of the easiest measurements to perform if you didn't have automatic power measurement capability in your scope. Simply connect a standard passive probe to the DC output signal. If you didn't have the automatic measurements, well, then you could just scale it, and I would suggest turning on AC coupling in order to just look at the output ripple and then measure volts peak to peak. If you do have the automatic measurements with the oscilloscope, you can press auto setup. It will automatically select AC coupling and then automatically select the volts per division, maximize the deflection here, and then give you an output ripple measurement, which is actually volts peak to peak. It also provides an RMS measurement. Often noise is measured in terms of RMS. Now, this particular power supply that I've got 1.7 volts of ripple. That is not good at all. We've got a demonstration power supply, and so it wouldn't be considered a good power supply, but it's good for training people on how to use our various measurements. This is, I mentioned earlier, a unique measurement capability in Agilent's oscilloscope. Is called the power supply rejection ratio, PSRR. Some people call it power supply ripple rejection. And what it does is it provides a measure of how well a device, typically a DC to DC converter, or often an LDO, which stands for low voltage dropout regulator, how well does that device reject various frequencies. So if your input signal is modulated and changing, how well is the output regulated, and if that input signal is modulated, at what frequencies, how well does it reject various frequencies. And the formula for computing power supply rejection ratio is 20 log Vin over Vout. Now you're probably familiar with 20 log Vout over Vin, which is a gain formula. This is just the opposite, because what it's measuring is not gain, but it's measuring rejection, and it's going to be measured in terms of dB. Now the type of instrument that you typically use for this type of measurement is a network analyzer, which can be very expensive, but it can also be performed with an Agilent oscilloscope because we have a built-in generator. And the way the measurement is performed, so here's your DC input, here's your volts AC. This is our generator. It has to be input into that DC input. It has to be coupled in. It has to be summed. There are network analyzer components that will do this summing, or you can create your own summing network using inductance and capacitance. If you just connect the generator directly without coupling it in, capacitive coupling, if you just connect this generator directly to this point without these inductive and capacitive elements, the DC input looks like a low impedance. It's going to short out your function generator, and the function generator looks like a low impedance to the DC input. So you've got to create a summing network or purchase some network analyzer components that do this for you. So let's take a look at the how it's performed on the Agilent oscilloscope. Again, we have a built-in function generator as well as arbitrary waveform generator. It has to be coupled into the power supply. And then what the generator does when you click on apply, it will sweep from a very low frequency to up to 20 megahertz, and it will measure the AC input. So it's sweeping it with a sine wave signal, and it does it rather slowly. It's not as fast as a network analyzer, but this is what I call a poor man's network analyzer. Now, it's not as good as a network analyzer. The scope can measure to about 50 dB. Now, the type of probes it's going to require, typically the input is being modulated. In this case, this is the yellow waveform, a relatively high-level signal. It may be a half a volt peak to peak. You can just use one of the standard probes that ship with a scope. The output signal is typically going to be the amount of modulation that you're measuring coming on the output is going to be extremely low, especially if it was 50 dB of rejection. This is probably going to require a one-to-one probe in order to get the most sensitivity. And so the purple waveform here shows the results. In this case, I was measuring a high-pass filter, and so it was getting approximately 50 dB of rejection in this area, and up at 20 megahertz, I was measuring about 13 dB. Transient analysis. This is an important measurement. Whatever final product you have, it could have load changes. Just think of perhaps such as an automotive system. There are things switching on and off, motors switching on and off, actuators, different mechanical things where the load can change significantly. And you want to be able to characterize load changes. And the way you would do that, you could have an electronic load that you could vary and change. You may want to go from the worst case maximum load to whatever you determine is your worst, best case minimum load. And what it measures is when you have a sudden change in load, how long does it take the output DC signal to settle back to within a certain percent. So what I'm showing here in this top screen here is actually the help screen of the scope. With the scope, any of these measurements you can press and hold, such as this soft key right here. If you press down on this where it says you want to analyze do transient analysis, if you press and hold that key down, this pops up and gives you a description of the test. And it shows you how it will measure when the DC output signal deviates within whatever percent you specify. Let's say you say 5%, to when it comes back to within 5%. That is the transient response. So again, this is a transient type measurement. It is single shot. The scope provides step-by-step instructions. It will tell you to press, it will tell you change the load, press next, and then it will set up the single shot measurement. So what we see here is we're going from a low current to a high current. So we're going from a minimum load to maximum load. It sets up triggering when that current waveform transitions between those two states. The yellow waveform is the DC output. And what the scope does is it sets it to AC coupling and sets the scaling such that you can see any changes and then automatically measures, in this case from this point where it deviated more than the percentage that we specified to when it came back to within that percentage. In this case, we measured a transient response time of 1.68 microseconds. Turn on and turn off time are also transient type measurements. When you flip the switch on your power, how long does it take to ramp up and get to its final level? Again, the scope provides step-by-step instructions. I'm not showing the connections diagram here, but the way you would connect, you have your AC differential probe on your AC input. You'd probably have a 10-to-1 passive probe connected to the output. And so the yellow waveform is the AC input voltage. The green waveform is the DC output voltage. So we've been talking a lot about current, showing the current waveform is the green waveform. In this case, the green waveform is the DC output. So here you can see it when you flip the switch, the AC begins turning on, and you go from a low voltage output to a high voltage output, and it automatically measures that time from this marker to this marker. In this case, we measure 31 milliseconds. Now, this measurement could be performed manually. What we find is A lot of engineers simply are not proficient in setting up the oscilloscope to make these measurements very quickly and proficiently. So this is just an aid in order to do it automatically. Turn-off time does just the opposite from when here you can see the yellow waveform is the AC input. When you flip the switch, this is when you turned it off, and there you can see the with some capacitive output filtering, it maintains that level and then drops. In this case, it took for this particular power supply almost 400 milliseconds to decay to about 10% of the final value. And you can set these percentage where you want to measure to. The last measurement we're going to talk about, this is pretty much the bottom line. How efficient is your power supply? This is a input versus output or output versus input measurement. This particular measurement requires the most probes. So you've got to connect a differential active probe on the AC input, a current probe on the AC input, and then you can probe the output, DC output, as well as a current probe on the DC output. And then the scope, when you press auto setup, will automatically scale these waveforms and give you your efficiency. In this case, the efficiency of this power supply is not all that good. It's about 78%. Now, as I mentioned, this takes multiple probes. This particular measurement could be set up and performed in 2 steps. Say, for instance, you only have one current probe. You could perform the measurement on the input, measure the input power. That is the real power, which if you go back to the power quality measurement when we were characterizing the input, that is the real power. You could then take the connect your probes to the DC output and measure the output power. That's going to be very easy to compute because it's going to be in this case we're showing a DC signal here and a DC signal here. You're going to have DC power, and then you could just compute the power yourself if you don't have enough probes to perform this automatically. So let's summarize. Switching power supplies are in every product, or not switching power supplies are in every product. And you want the most efficiency possible, and so you want to be able, you want a tool that allows you to characterize and make measurements on your power supplies so that you know the quality of your power supply. And now, typically within most organizations, there's what we call the power guy. He's a specialist in designing or characterizing power supplies. We've got a couple here at Agilent in our oscilloscopes lab, and those are the guys that spend all their time. And to be honest with you, the power guy doesn't get a lot of respect because he's not working on leading edge, high-speed digital circuitry that's flying at picoseconds. But the power supplies today are very complex devices, and it's not that simple as it was way in the past. So my suggestion is give this guy some respect. He knows a lot of things other people don't know. These are some of the power measurements we talked about that are available in Agilent's oscilloscopes. We've shown examples in most of them. The one we didn't show an example of that people would probably consider a very important measurement would be safe operating area. That's also available from Agilent with a PC-based software which ships with our solution. The scope and the power measurements option is just part of the solution. As we talked about, power measurements take a lot of specialty probes, current probes, high voltage, differential active probes. These I've highlighted here the variety of probes that are available from Agilent for performing power measurements. The ones here in bold are the ones that are most popular. Most of the measurements, I believe, that I took showing these screenshots were using what I call the 1147 50 megahertz 15 amp current probe and the 2790 100 megahertz 1.4 kilovolt differential active probe. Those are the ones that are the most popular. So the scope is just half the solution. The other half is probing. As far as technical resources go, I've just highlighted one application note that we have available. It goes into more depth on the issues that we've talked about today. This is the Agilent publication number. You could jot this down right now, and then if you just go to agilent.com, there's a search box up in the upper right. Enter that number, and this particular app note should pop, and then you could download it, print it out, and read it. Although, also, I think at the conclusion of this webinar, there is going to be a follow-up email going to you, and there will be a link that will take you directly to this particular app note. The scopes that screenshots that I used today were from our newest InfiniiVision X Series oscilloscope. This is our newest one, the 4000 X Series. It has a very large screen, touch screen. Also, these measurements are also available on the 3000 series. It's got a smaller screen. It's not touch screen, but it performs the same exact measurements. The InfiniiVision X Series, there's the 2000 X Series. Ranges from 70 to 200 megahertz, which is typically enough bandwidth for performing these measurements. However, it does not have the automatic power measurements that we've shown here today. Both the 3000X and the 4000X series scopes have this automatic power measurement capability. So those are the ones I would recommend. So at this point, I'd just like to open it up for any questions you might have.
Well, thank you, Johnny. As Johnny mentioned, it's now time for Q&A. If you haven't done so already, you can send questions in writing any time. We'll put that through to the Q&A functionality at the bottom of the WebEx meeting tab, and we'll do our best to answer those during the session now. If we run out of time, we may come back to you a little later. While the questions will be public, the answers will also be public, but we'll keep your identity private. During the course of your presentation, Johnny, and I have to say thank you very much for a great presentation, we have had a couple of questions that have come through. The first one here is, what kind of performance should I be looking for in an oscilloscope to perform power supply measurements?
Okay, well, let's flip back to this slide that I just showed. Typically, 100 to 200 megahertz is going to be sufficient bandwidth. You don't need one of these bleeding edge, expensive, high-performance oscilloscopes to perform these power supply measurements. Now, you might say, okay, my input frequency on the AC input, I think Europe is primarily 50 hertz, and the U.S. is 60 hertz, so you certainly don't need a high bandwidth scope to make those measurements. The switching circuitry might be going up to a few hundred kilohertz. Again, you don't need a lot of bandwidth to measure that. However, it's the transitions, the switching speed of those switching devices, the rise times, the fall times that are important. And so that's why you might need 100 to 200 megahertz. Now, if you want to know what is the lowest price point you can get into, a 3000X series 100 megahertz scope. I don't have the European price in euros, but in the U.S., if you got just a 2-channel scope, 100 megahertz, it's a little under $3,000. Plus, you have to add on the power measurements option if you want to do this automatically, and that's about another $1,500. Now, that's for a 2-channel measurements. All the measurements I showed today, except for one, can be performed with a 2-channel scope. The only measurement that requires a 4-channel scope is the efficiency measurement, which, as I mentioned when I was going over that, you can actually do that in a two-step process. So you don't need a high-performance scope. You can get away with 1 to 200 megahertz. The one thing I want to caution you is, as I mentioned earlier, the scope is just half the solution. The other half is the probing, and you'll find that these specialty probes are not inexpensive, and they could cost as much as a low-end scope.
Okay, thank you. Well, there was another question I had here about how many probes are required for the various power supply measurements you've shown today.
Typically 2 specialty probes. So that would be, if you're going to measure the AC input as well as if you get a high switching voltage across that transistor, let me flip back just a couple of slides. You're going to need a high voltage differential active probe, and then you're going to need a current probe. So these are the 2 primary specialty probes you're going to need. Now the scope itself will ship with standard 10-to-1 passive probes. And so those probes, they're good for some of the measurements, like the DC output. If you're going to characterize the output ripple as well as turn on, turn off time, you can just use the standard probes that ship with the scope. The PSRR, power supply rejection ratio, that's where you're probably going to need a 1-to-1 passive probe. This is the one that we would recommend. It's not terribly expensive, but this is where your big investment is going to be, is in your current probe and your high voltage differential active probe.
Okay, thank you. Here's an interesting one. How do you get a clamp-on style type current probe around a PC trace?
You don't. This is where you're going to have to modify your device under test in order to make these current measurements. Now, one easy way to make the current input is typically you're going to have a power cord. Now, I probably shouldn't be recommending this because I'm probably going to get all sorts of safety issues thrown at me. You can strip back the insulation on the power cord and get a hold of that line wire within the insulation. You know, if you get that insulation stripped back, and you can easily clamp on to that particular one. Now, getting on to the current waveform going through the drain and source of your transistor, you're going to have to lift the leg or cut a trace and create a wire loop in order to get the clamp-on probe around that. Now we have the power supplies I made, the measurements I made on the power supply as a demonstration board. We actually laid out the PC board to create a loop, but you're not going to do that on your end product of your power supply. So you're going to have to do some modifications to do that.
Okay, thank you. The final question I have at the moment here is, how important is probe deskewing, and is the Agilent deskew fixture included with the power measurement option?
First of all, the deskew fixture is not included. That is an accessory that you have to buy. Now let me let's go back and see if I can find a particular slide. This one right here. So here we can see the voltage waveform ramping up and the current waveform ramping down. We're set up, I'm trying to see what the time base is. It says 72 nanoseconds per division. So there's not a lot of time between the voltage going up and the current coming down. Just a few nanoseconds of skew will significantly change your power loss measurements. Not this particular measurement. This is a slew rate measurement. It's making measurements only on the voltage waveform or only on the current waveform. The one measurement that is extremely important to deskew your probes is the switching loss measurements, where you're measuring that impulse of the power loss during that switching time. Now you can actually create your own deskew fixture. You could take a generator that generates a step, and then you could send it through a resistor, and then you could measure the current through that resistor and connect your probes there. And so you could do this manually, and deskewing manually is actually pretty easy. Oscilloscopes today, you can just set it up, show the rising edge of the voltage in the current waveform, and then there's a menu inside of let's say you're triggering on channel 1. Let's Say, for instance, that's this ramping voltage. The current would be ramping up, not like I'm showing here. It would also be going up. It might be skewed. You go into the Channel 2 menu, and then you can deskew. You can actually pull in that current waveform and make it align with the voltage waveform. So that can be done manually.
Okay. Well, thank you very much. I don't have any further questions at this point. If anybody else wants to ask some questions offline, please don't hesitate. Contact us on the address provided. In a few seconds' time, we'll close the webcast. An evaluation form will pop up on your screen. We appreciate your feedback, so please take the time to complete that. Johnny, finally, I'd like to thank you again for your presentation, and everybody else online, I'd like to thank you all for your attendance.